Yeah. Yes. Okay. So okay, so y'all can see my screen, right? Cool. Somebody. Yes. Okay. Now, how about if I do this? Can y'all still see this? Would somebody unmute and say?
Yeah, I think we can see it.
Okay. Perfect. Cool. All right. Well, I appreciate y'all helping me get set up. So first thing we're going to be talking about today is quicksort. So quicksort is in the class of comparison-based sorting algorithms that is the best possible case under the lower bound theorem, which essentially says that not best case, average case under the lower bound theorem. So essentially, quicksort is going to be one of several of log and log n sorts. And today we're going to be covering merge sort, maybe if we have time. There's a quick sort. So this is kind of its own class of like relatively good sorting algorithms. We've covered previously, y'all remember bubble sort, insertion, select. So these are like kind of relatively the bad sorts. So usually we start off by teaching the bad sorts just because it's easier to understand what's actually happening. And I think it's more difficult to understand what merge sort and quick sort do and why it's better. So I'm going to run through an example. So I assume you all have like seen quick sort at least a little bit. Um, I'm going to make a fictitious array. So this is just like, imagine we've got some kind of hypothetical array here. It's got numbers in it, and it looks like this. The whole paradigm behind quicksort is pivoting. So essentially, to use quicksort to sort an array like this, you have to pick one of the elements of the array to be the pivot point. So first thing is pick a pivot point. So obviously this raises the question, we've got 5 elements in this array, so which one of them should we pick to be the pivot point? That ends up being a much more difficult question than what is maybe immediately obvious. Just specifically because if we have an unsorted array, we don't know the median of that array. Like that, the median, the optimal place to split this list into 2 parts, we have no idea. So ultimately, we end up taking a guess. So for this example, let's say we split it on 2 being our pivot point. And so what we're going to do is we're going to traverse this array and we're going to look at each element of the array and compare it to 2. And depending on its relationship to 2, we're going to put it in one of 2 subarrays. So hopefully, if y'all's intuition has been building by now, whenever you see log n time complexity, some kind of bell should be going off in your head thinking like, okay, log of n, that means I'm dividing a list by 2 at some point. I'm splitting a list into 2. And as you can see, this is going to be intuitively a log n algorithm because right away we're breaking a list into 2 hopefully equal sublists. So I'm gonna prove that to y'all. For now, take my word for it. So essentially we're gonna be sorting this list into lists that are either less than or equal to 2 or greater than 2. So in this case, it's gonna look like this. 5, 8. Is that fair? Have I lost anybody? Everybody understands the steps so far. I think we have our PT with us. So if something that I do doesn't make sense, please ask in the chat. She'll be more than happy to answer your questions. Okay. So, anyways,
Can I add something?
yes, please.
So is it just like you randomly choose some number in a list, or it has to be some condition or something?
That is the question. So given that I haven't really explained quicksort all the way, I kind of wanted to hint at why this is such a big deal, randomly picking this pivot point. But I will say that is an excellent question. And that is the whole issue behind this sort, is where do you pick the pivot point? Ideally, you would want, like if this was a list of size n, the ideal scenario is that you split your list of size n into a list of size n over 2 and a list of size n over 2. That's ideal. That's not going to happen every time. So essentially, the ideal pivot point is the pivot point in which you have broken your list exactly into, which would be the median, which would be ideal. But again, given that this is an unsorted list of integers, we would have to calculate the median, and we don't want to do that. So for now, we're guessing. But excellent question. I'm sorry I'm not going to go into too depth for like the next 10 minutes or so, but I will answer that question thoroughly. So we repeat this process. Quicksort is recursive, and one way that you can like intuitively tell that an algorithm is going to be recursive is if you're repeating the same process at each iteration with an input that you got from the previous step. That kind of gives you like a little hint that maybe a recursive definition might be a good way to solve this problem. So here, let's pivot around. Let's pivot around 1. And let's just say we get these 2 lists. I think that looks right. And then for this list, let's pivot around 8. Again, I'm just picking randomly. There's no rhyme or reason here. We get 5, and 8, and then we get 9. And let's see, let's pivot around 8. So we get and 8. Okay, and as y'all can see clearly, the list is now sorted as these leaf nodes. So once you reach a list that has a size of 1, these are all sorted by themselves, right? So a list of 1 element is always going to be sorted, right? And then basically, if you just traverse reading these nodes one at a time, like this is your 0 index, 2, 3, and 4, you've now got a sorted list, 2, 3, 4. It's now in order, and it's sorted. Okay, so that's essentially the paradigm behind quicksort. And so somebody asked a question: why do you pick randomly? Well, that's a tough question to answer. But given the same list of integers, I can pick different points and show you what happens. So I think it was this, right? Yeah. So I just, for the sake of the example, happen to pick reasonable pivot points. But given that the pivot point could be random, you could pick a pivot point here, for instance, and then now you've got this list and this list. And then imagine we accidentally pick a bad pivot point again. So we pivot here, and then now we've got this. And let's say we pick a bad pivot point again. We pivot around 5. And then that's going to give us this. And just for the sake of giggles, let's assume we do it one last time. Okay. So what happened here? Is this still the same time complexity as this algorithm? Like, did we do just as good of a job as we did here? Clearly not, right? Like, with zero math, like with zero logic, zero proofs whatsoever, you can visually just tell that this structure that I just drew is just bigger than this structure. Like if you were to just look at the size of this tree versus the size of this tree, this one takes up the full page, and this one is like kind of like half of a page maybe. This one has 1, 2, 3, 4 levels, and I think this one has 5 levels. So right away, it becomes clear that where you choose this pivot point is going to drastically affect the performance of this algorithm. So specifically, this is known as the worst case. This is the worst case. So in the algorithm, if you pick the worst pivot point consecutively over and over and over and over again, you have reached the worst case. Whereas this one up here, this is this, I'm going to call this average case. And the difference between the average case and the worst case is how you make this choice right here. How you pick your pivot point. That's what separates the two cases. And we're going to see today that the running time for the average case is log of n, n log n, my bad, y'all. And the worst case is going to be O of n squared. So this is an example in which the big O notation actually depends on random chance, kind of. And there's two different potential outcomes depending on which one of these decision trees you go down, essentially. So I'm going to start with proving the worst case time complexity. So essentially what's happening here in this picture is we've got this is a list of, actually I'm not going to use that notation yet. So we've got essentially at this stage we've got a list of size n, and then here we've got n minus 1 and then a list of 1, and then we've got n minus 2 and a list of 1, and then n minus 3 and a list of 1, and then n minus 4, oops, sorry y'all, and a list of 1. So looking at this, it becomes pretty clear that this is the arithmetic sum, right? So if n is 5, we've got 5, 4, 3, 2, 1, and that's how many comparisons we're going to be doing at each level, right? At this level, the level of 5, we're going to be doing 5 comparisons based on the pivot point. At this level, we're going to be doing 4 comparisons based on the pivot point. We're going to be doing 3 comparisons based on the pivot point. You get the idea, right? And so essentially the runtime of this can be summed up as the arithmetic sum, which is, y'all have seen like 1 plus blah, blah, blah. And so we get to n, which is going to be something on the order of like n times n plus 1 over 2, which is roughly O of n squared. So are y'all happy with that? That's not the most rigorous mathematical proof that is possible for this case, but just to help you build intuition, you can see depending on like where you are in the structure, like if you're here at this level, you're doing 5 operations and then 4 operations, and hopefully you can kind of see that this is going to scale within quadratically, right? Because you've got 5 plus 4 plus 3 plus 2 plus 1. This is the same runtime that you had for like bubble sort or selection sort. This is the formula for that, and then that's going to be roughly n squared. So this is worst case. It's kind of the intuitive proof. I hope I can't see y'all's chats, so please consult Oma, our PT. She'll be able to answer. That doesn't make sense, I apologize, but that's like your rough intuitive take. So let's give a more formal definition. Let's give a more rigorous proof. So this was like I'm gonna call this like intuitive proof. So this is like maybe not good enough to like put in a textbook or something, but that that should hopefully get you started. So recurrence relations, I very quickly I'm going to detail just like a general formula for all recurrence relations. So recurrence, actually I'm gonna write it down here. So recurrence relations, their time complexity formulas are all going to look something like this. So you've got a recurrence relation formula. And so this will be different depending on the algorithm that you're looking at, but usually it's going to look something like this. So T of n, and don't get confused about why it's T. Like you've seen O of n, you've seen F of n. T, I believe that's the computer science convention, specifically because it stands for time complexity. I think that's my guess. I don't know if that's right or not, but that's how you can think about it. So T of n is going to be equal to, sum A times T, and it's not necessarily going to be division here, but just for the sake of argument, It's just, you know, O of 1. So usually your recurrence formula is going to take something like, it's going to look something like this. And specifically, let me bring this down a little bit. I'm going to label these parts to actually maybe describe what it is we're looking at. So here, right here, this is your time complexity for input in. Right, I think that's fair. I think that's relatively obvious. What's not so obvious are these next terms. So this is going to be number of subproblems. And then this is going to be input size for each subproblem. And then this is going to be time complexity for this step. Okay, so again, I hope I haven't lost anyone. I know it's maybe a little bit daunting to look at this, you know, new formula that you'll probably haven't seen in other classes before. But intuitively, I think it does make a little bit of sense. So on the left, we've got T of n, which is our recursive definition for time complexity. A is how many subproblems we have. This thing in the parentheses is, oh man, I'm so sorry, y'all. I'm so sorry. This isn't a T. This is an N. If y'all were confused, I apologize. I'm gonna rewrite this whole thing. Man, okay. There you go. Okay, so if anyone was confused, that's absolutely my fault. I completely apologize. But so intuitively, it kind of does make sense, right? Like, how many subproblems do we have, and then how big is the input to each subproblem? So y'all take a second to look at this. Convince yourself that it kind of makes some sense. But anyway, so back to quicksort. So we were just talking about the worst case. So what that is going to look like is the worst case for quicksort is going to be, I'm actually going to make a definition like this. So this is kind of like your general template. I'm going to make a definition. So we're going to have one subproblem, which is going to be T of n minus 1. We're going to have one subproblem that is T of 1. And then we do O of n comparisons for each level. So I hope that's fair. I hope that kind of makes some intuitive sense. I'm going to go back to this picture that we drew up here. So for the worst case, as you can clearly see, we are going from step 1 to step 2. We're going from a problem, this would be T of n, and we're splitting that into a problem of n minus 1 and a problem of just input 1. So hopefully that makes some kind of sense. And we did n comparisons around the pivot. So that's just kind of represented by this formula right here. As in for each comparison, we count that. So we got O of n, and then we got our two little subproblems here. Specifically for solving a recurrence relation, usually your best bet is to just start plugging different things into this recurrence relation. So specifically, this is a formula. So we could just plug x in here, plus T of 1 plus O of x, right? So this is completely valid. We can absolutely manipulate this equation however we want. So what happens when instead of an n input here, what if we change this to an n minus 1? So T of n minus 1 is going to equal T of n minus 1 minus 1 plus T of 1 plus O of n minus 1. Okay, so let's reduce this a little bit. So we got T of n minus 2 plus T of 1 plus, I'm just going to say this is roughly O of n. I think that's fair. I think we proved that before. Okay, so what did we just do? We just abstracted this formula right here to the point where we can put in any kind of input. And maybe y'all can see where I'm going with this. I am angling at replacing this term. So what we've just done is we've defined this term that appeared in our original equation. We've defined what that is. So now if we want to, we can substitute this equation that we've just come up with into this top equation. I think also something worth noting is that this T of 1, if you're wondering what that T of 1 stands for, that stands for when you've got like, this is T of 1, that's your base case. You've got a list of 1. And for the sake of this proof, let's just go ahead and say that the time to sort a list of 1 element is 0, because we can just assume that it's automatically sorted. And this is our base case. So let's just make that assumption. I'm going to go ahead and move this to the top. Probably should have done that first. So again, I hope I haven't lost anybody. Right now, we're just manipulating stuff. It's nothing I think y'all can't handle. Wow, this is a total mess. I'm so sorry, y'all. Bear with me. So this is our base case, which I think, I think this kind of does make some intuitive sense, right? Like a list of size 1 is already sorted, and that's the whole point of doing quicksort, is that we're trying to reach lists of size 1 because we're abusing the fact that they're already sorted. Okay, yes. All right. Okay, so where were we? We can assume that this is 0. So let's rewrite everything and make it clean. So T of n, we do the substitution here, is equal to T of n minus 2 plus O of n plus O of n. So that is equal to T of n minus 2 plus 2O of n. So again, I hope I haven't lost anybody. I think this is fair. I think this is a fair step that we just took right here. Now for laughs, what if we redefine this term and substitute that in? So we got T of n minus 2. And from our original formula up here, we know that that's going to be T of n minus 3 plus O of n comparisons for that level. So let's go ahead and redefine n equal to T of n minus 3 plus 3 O of n. Okay, so are y'all seeing a pattern here? Because I think I'm starting to see a pattern here. So the first formula that we had, we've got T of n minus 1, and then you can think there's like a coefficient of 1 right here. And then for the second iteration, we have T minus 2, and then you can see we've got a coefficient of 2. And then for this one, we've got T minus 3, we've got a coefficient of 3. So as you can see, what we're really working towards is a general formula. So the general formula that we have here is T of, and I'm going to use K, that's just kind of like, that just happens to be the convention for this type of proof. So T of n minus K plus K times O to the n. Okay, so again, I really hope I didn't lose anybody. I know this is a lot of math, and I know it's Sunday. So if you're looking at math on Sunday, good for you. I hope you have not fallen off the bus. So essentially what we've done is we have defined this recursive problem to be this formula, which is right here. And we have manipulated this original formula right here into this general formula. So I'm gonna call this the general case. Actually case is confusing because we've got a best and worst case. So I'm just gonna call that general. And then I'm going to rewrite our original formula. So our initial guess was that the formula should look something like this. So these are the same. All we did was algebraic manipulation. So these two are equivalent. But for our purpose, we're going to be working with this one. Okay, so this right here is our recursive. This is our recursive term. Recursive term, right? Y'all remember from the general formula up here that when you're looking at a recursive problem, this is going to be what actually does the recursion. So the recursion is right here. Okay, so now that we have this general formula, what do we do with it? Well, ideally, we're reaching the base case, right? That's what's actually happening when we're doing the recursion, right? Because when we start with a list of this size, we're working to get towards a list of size 1. So in this formula, let's work to get our base case. So remember, our base case was t of 1 is equal to 0. So when is it that our recursive term is going to be equal to this base case? So t of n minus k is equal to t of 1. So when does this happen? Yeah, when does this happen? That is when our recursive term is equal to our base case. Well, hopefully should be relatively easy to see that given that t is the same function and both sides of this equation, this is going to happen when n minus k is equal to 1, and it doesn't take much calculation to see that n is equal to k plus 1, or better yet, k is equal to n minus 1. Okay, so now that we've solved for k, let's go ahead and plug k into our general formula and see what that looks like. So remember, our general formula was t of n is equal to t of n minus k plus k times O of n. Let's rewrite that as t of n equal to t of n minus, and k is n minus 1, remember, n minus 1 plus n minus 1 of n. Okay, so let's see. Yeah, I wrote that small, so sorry if that's difficult to interpret, but let's go ahead and do some simplification. So we know that this is t of 1, and we know that that's 0. So now we're looking at t of n is equal to n minus 1 times O of n, which is going to be O of n squared minus n, which is 2O of n squared. Okay, so that was a lot. That was a lot to prove something that was, honestly kind of visually obvious, right? Like looking at this algorithm visually, you can kind of just immediately, like intuitively sense that we're looking at a quadratic algorithm, right? Because you've got pretty much a list of size n, like this is relatively size n, and then this is also relatively size n across the whole list. And you do that n times. So intuitively, you can think like, oh, relatively list of size n, and you do that n times, you can think relatively n squared, right? It didn't take very long to figure that out visually. This proof took considerably longer, which I think that tends to be the case when you're thinking about proofs, is like figuring out what the right answer is a lot easier than proving to yourself that this is the right answer. But hopefully you should have no doubt in your mind whatsoever that we have proven this is the time complexity of the worst case. Okay, time complexity, worst case. So I hope that makes sense to you. I hope you can sleep well at night having seen this, having seen these steps. Like essentially we wrote a general formula. We used math to manipulate that general formula until we got something that looks like this, which gave us a term that we can solve for. We solved for k equaling the base case, plugged it in, got an answer. Okay, so that was worst case. Let's talk about best case. So specifically, I said earlier, I kind of hinted that the best case, average case is going to be something similar, which is really complicated. Maybe I'll cover it in a coming week. The best case is going to be when you split your input by 2 every time. So just draw a little picture of what that might look like. So imagine you've got so this is your, imagine this is your best case. Oops, my bad. Okay, so this is your input. Say you got some kind of array here. Actually, I can redo that. I can do that better. I'm sorry. Man, okay. I'm sorry. I just I want to be picky with these things. Okay. So imagine this is our original input. Best case is when we split that input into two equal subproblems at each step. So in this case, I think I drew 8 elements. So the best case would be splitting this into two problems. And then as you can see, you can just keep doing this. So essentially, we're going to have something that looks like this, something that looks like this. And this is the ideal pivot point. So if we continue to guess the best possible pivot point over and over and over again, eventually we're going to reach the base case in which we have lists of 1. And remember, the whole idea here is that we're trying to reach lists of 1 because lists of 1 are always sorted by definition. So this is going to be T of n over 4. This will be T of n over 8. Okay, so intuitively, I'm going to start with intuition first because I think, again, the math is important and it definitely helps you conceptualize what's happening, but it's not the be all end all realistically. And it's, I think, a lot harder to grasp. So intuitively, you should be able to see that we have formed a tree structure here. So because we're dividing this list by 2 each time, we can divide this list by 2 log of n times. So again, sorry if that's like, maybe not the most obvious thing at first, but that is the definition of log. Like how many times can you divide something by some base, right? So for this instance, the height of the tree is going to be based on this input size, right? Like obviously for a bigger input, it's going to take more divisions of 2 to reach this this base case, right? So in this picture that I drew, n is equal to 8. And as you can see, height of the tree seems to be n plus 1. I mean, not n plus 1. It seems to be log of n plus 1. Seems to be. But for our purposes, we're just talking about big O. So I'm just gonna say it's roughly log base 2 of n. So hopefully that is not too far out of the park, seeing that it's going to take log of n times to split this list. And then let's talk about the average operations that are happening here. So if we pick a pivot point here, then on this, like per level, this level is going to be O of n operations to get to this level, and then this is going to be roughly 1/2 O of n, and this is going to be roughly 1/2 O of n, right? Because we're pivoting across 1/2 of the elements here, and then we're pivoting across 1/2 of the elements here. So in total, this whole level still totals out to O of n, and this whole level still totals out to O of n. So what have we done here? We have essentially made a visual proof. Like this is a geometric proof, right? Like y'all know area is like height times width. You can kind of think of this as height times width, right? So we define height to be log of n. We define width to be O of n. So naturally the area of the structure would be n log n. And that's the intuitive proof. Again, probably doesn't belong in a textbook, is not the most rigorous definition possible, but let's just say total runtime is equal to the number of levels times cost per level. I think this is fair. I mean, hopefully y'all are tracking with how I got this. And then we know these numbers. So log of n, number of levels and cost per level is n. So we're looking at, man, I keep doing this. I'm so sorry, y'all. I'm so sorry. So we're looking at n log n. So again, like we did before, this is not your rigorous proof that this is n log n. Like this is what we're looking at. I kind of said just, take my word for it. This is, you know, maybe one step removed from taking my word for it. Maybe that'll kind of like show you if you pick your pivot point well, you're dividing the list each time. The more astute of you might have noticed that this also is merge sort. Merge sort is like almost kind of like a sub case of quick sort, where you just intentionally brute force divide the list into two each time. And then sort on the way back up. So the two algorithms are pretty similar, and the runtime for merge sort is always equal to the best case of the runtime for quicksort. Those two things are identical. And so if y'all are comfortable with the merge sort proof, that can be used here. It's literally the same proof. But yeah, so this is your best case quicksort. Okay, so if anyone has any questions from me that I can see, please unmute yourself. Because I think this is fair. I think this is, you know, relatively kind of intuitive. If I've lost anybody, I would like to know. So okay. Well, assuming y'all are all tracking, I hope y'all are all tracking still. Let's go ahead and prove this. So back to our wonderful recurrence relation general formula. Remember, we've got our actual recurrence relation term, we've got how many subproblems, the size of each subproblem, and then the time complexity for this step. Let's go ahead and write another one of those. So looking at this, seems like at each iteration, we're going to have two subproblems of size n over 2, and it's going to be O of n per step. So let's go ahead and let's go ahead and formalize that as this. So let's just say this is best case. So hopefully this is fair. As you can see, we've got two subproblems. Each subproblem has input n over 2. Let's see. And then, as you can see, this is the cost per step, right? Because for each pivot point, in this case, it's going to be cost to compare against the pivot point. Okay, so that's why the formula looks this way. Let's go ahead and do what we did earlier. So I'm gonna maybe go a little bit faster than I did last time, so hopefully you can stick with me. So t of n is equal to 2 times t n 2 plus O of n. What happens when we solve for this term, right? So t of n minus 2, what happens when we plug that into this formula? Well, we end up getting 2 times n minus 2 over 2 plus O of n. And sorry, I'm not going to be speaking much for this. I'm just going to actually solve it. So got 2t n minus 4 plus O of n. And let's go ahead and substitute. Sub that in. So now we've got t of n is equal to, and this is what we're substituting. So we've got 2 times this plus O of n, which looks like 2 times 2t of n over 4 plus O of n plus O of n. And that works out to 4t of n minus 4 plus 2 O of n. Okay, so sorry for the speed at which I did that. I mean, I trust y'all's algebra skills, so I think where people would get confused on this step would potentially be like what these numbers mean, not how you actually manipulate the formulas. I think the manipulation is pretty easy. So let's think about this intuitively. So we've just said that t of n is equal to 4 subproblems of size 1/4 the original input size, and we have done 2n comparisons to get here. So looking at our tree, that seems to be correct. It seems that we have 4 of these problems, And it seems like we've done this O of n comparison once and then twice. So that seems to be intuitively correct. I think this is good. This makes intuitive sense. And let's go ahead and do it one more time just for laughs. So sorry if the bus is moving too fast and y'all falling off. I'm gonna do it again, so maybe y'all are gonna see the pattern one more time. Okay, so this is plugging these things into the original formula that we wrote from up there. So if you're wondering why I can just calculate this so quickly, that's because I'm taking this from this. Yep. And so let's do some algebra. And then let's sub it back in. So here's our substitution step. So T of n, and yeah. Oh, and I maybe have made something of a misstep here. Maybe I should go back and clarify. I'm just kind of shorthanding this, saying, oh, it's relatively O of n here. But if you wanted to be really picky, technically at this step, and I'm so sorry to be moving at the speed of light, y'all. Like that's my bad. Technically, we're looking at this, because technically for each sub problem, you're only pivoting half the list, right? So technically, this constant multiple here, this gets multiplied by this, which is why you have this. So for consistency's sake, I apologize about that. So let's just be consistent. Let's call this what, 1/4 of the list, and then 1/4. Yeah, something like that. Okay. Well, I'm sorry to have been inconsistent, confusing. It's definitely not not my intention at all. Okay, so where were we? N is equal to 8 plus okay, well, I'm just gonna start over. I'm so sorry, y'all. See, so T of n is equal to 2 times T of n over 2 plus n, and then we said that T of n over 2 is equal to 2T n over 4 plus 1/2 O of n, and then we redefined 2 times okay, so again, sorry to repeat that so hastily. That is completely my bad, y'all. I apologize. 8 plus 4. Okay. Okay, so if I lost you because I left off this constant multiple, I'm so sorry. Like legitimately, I'm so sorry. But the proof starting here is consistent. So this is consistently notated. You can kind of see this one makes intuitive sense too, right? Like T of n minus 4. The way that this step kind of looks a little bit like this step. And because these steps look kind of similar, you can see that there's a pattern that's starting to form. So the pattern that's starting to form is we've got this general case. Okay, so this seems to be the formula that we were looking to derive. So let's say it's kind of like our general formula. And let's remember that our original formula was this n over 2 plus O. So after some algebra, we have gotten to this step. So this is the whole point. We were looking for this, and we've derived it. It's very similar to the derivation we did. Where is it? Up here, how we were given some kind of original formula, and then we derive some more general formula. It's essentially the same idea down here. And now we solve for the base case. So again, the base case, we're going to call that T of 1 is equal to 0, which is like saying a list of size 1 takes no time to sort. So when does this happen? Well, that's when our recursive term is equal to the base case. So go ahead and write that. N over 2 to k is equal to T of 1. So when is n over 2k equal to 1? Well, that's when n is equal to 2 to the power of k. And then you can take the log of both sides. Again, sorry if I'm speeding through this. And then by property of log, you know that, oops, my bad. By property of log, you know that log of something raised to the same power is just that thing. Okay, so now that we've defined k, and again, I'm sorry if I just blasted through this step. This is algebra. Oh man, I can't spell either. Algebra. Okay, so this algebra. Yeah. So I'm not gonna. Y'all don't need to know why that is the case. Like these math things that I just said, but if you understand math, hopefully this is helpful. Otherwise, just kind of take my word for it that this is k. And then now let's plug that back into our formula that we had before. So our formula was t to the n is equal to 2 to the k, t of n minus 2 over k plus k times O of n. So if you plug that in, we get 2 to the log n. Oops, my bad, y'all. Let's see. 2 to the log n times t over n. And we decided this term was going to 0. So we've essentially got n times 0, and that's 0. So really, we're just looking at this term. So t of n is equal to log of n times O of n, which we did it, finally. After all that work, finally got there. Okay, so that was a lot. That was a very strenuous proof, very concrete proof that the best case is n log n time. The intuitive proof that we gave earlier, being this one, this is enough to convince yourself that the runtime is n log n. I think if you can look at the picture and see we've got log n levels, the cost is O of n per level, that should be enough to prove things to yourself. If you want a rigorous mathematical definition, here it is. So yeah, thank y'all for sticking with me. This has been Quicksort. So as just kind of an overview of what we talked about, we've kind of got like generally good algorithms and generally bad algorithms. The reason we teach you the bad ones first is because they're a lot easier than this. We haven't even talked about what the time complexity for the average. We haven't done this proof. This is the hardest proof. So if y'all want to see that, maybe I'll make a video doing that. But that proof itself is like that one. This is a monster. And I don't like it, but y'all will probably need to know it at some point too. So maybe we'll come back to that later. But essentially, Quicksort works by picking a pivot point and actually pivoting around that pivot point, doing the same thing at each level until you reach lists of size 1, which by definition are sorted. And as you can see, conveniently, they're sorted in order. Depending on where you pick that pivot point, you either do a better or a worse job of sorting your list. So if you pick the pivot point to be the end, instead of breaking up your subproblem into size n over 2, you break it up into n minus 1 and 1, and then so on and so forth. The recurrence relation is going to be a general formula which looks something like this, which is, the time complexity for input n, the number of subproblems, the size of each subproblem, and the complexity for each step. Given that this is your general case, like this doesn't have to be division in here. This could be subtraction, whatever it is. This is our attempt at defining a general case for the best case. And as you can see, after some algebraic manipulation, we get something that looks like this, which is not too far off from the original. We can solve for what this k is. We can solve for this k value. We know that k is going to be n minus 1. Plugging that in, we get roughly O of n squared for the worst case. And then same thing with the best case. So the best case, which is also identical to the time complexity for merge sort, pretty similar idea. If we just happen to pivot the list perfectly at each iteration, we're breaking the problem into this problem, and we have 2 of them. So hence our formula is going to look like 2 of these problems, because in the picture we drew 2 of these problems. As you can see, intuitively, we can just kind of automatically understand that we've got log n levels and the cost is n per level. So this is like intuition that we can prove this, but if we wanted to be mathematically stringent about it, we can do some mathematical operations and get this general formula here. We can solve this general formula for k. K is equal to log of n, you plug it in, boom. So thank you. If y'all have stuck with it through these mathematical proofs, y'all go like take a break or something. I feel like this is like heavy lifting. It just happened. Okay, so see, I'm gonna stop sharing. So does anyone have any questions? Don't be shy. Someone says thank you. Yeah, I appreciate you for being here. If anyone has any questions whatsoever, you can shoot me an email. I'd be happy to explain this stuff. Be happy to walk you through the steps.